over the original data and come out with a high quality cluster. And that is an unusual property of Lloyd algorithm heritage k-means clustering things. And we wanted to scale on the order of k times n at worst. And in fact, the final scaling factors are more like k log of, or I'm sorry, n times log of k. So it's even better than what we're talking about here, depending on how you define what k is. But it's quite aggressive in terms of scaling. I'm sorry, we did not want to scale as badly as k and n does, k-means does. The total scaling here is more aggressive than this. The per row scaling is essentially constant time. Now, the rationale for building this scaling, this stuff, is to build a nearest neighbor modeling system. Nearest neighbor is pretty simple. You find the nearest things, and you assume that a new thing that is near these old things will be like the old things. Just basically simple consistency of the universe sort of thing. It's easy, conceptually it's very easy, but it's hard because you have to find all of the near things. And in financial world, because the objective variable you're looking for, something like fraud, is a very low base rate, you wind up having to sample the nearest 50,000 things, not the nearest one or the first nearest 5. The nearest 50,000, you have to retrieve that back, you have to average those, and you have to do that in something like, on average, a millisecond, or a few milliseconds. If you're sampling, searching 1 million things or 100 million things, that can be hard. Pick up the phone. That's an assertive phone. And so there's a stunning amount of math that goes on in a K&N searching algorithm. If you actually multiply it out, if you're trying to do 20 million queries against 25 million vectors, and you do it with brute force, you've got tens of millions times tens of millions times, say, 1,000 floating point operations, and that's expensive. That's a lot. 10 to the 15, 10 to the 17 floating point operations in the brute force space. And the initial prototype took 6 hours to do 3,000 queries against 200,000 elements. And that's how fast the customer wanted to do 20 million queries against 25 million reference vectors. So we're a nice, even million times too slow. How bad is that? Come on. I've delivered projects that were that much too slow. I'm sure. But this one, they really wanted it to be better. Now, there was some advantage there because the initial prototype was implemented in such a way that we could get 1,000x speed up without even trying, just by really implementing it as opposed to just experimenting with it. But there's still 1,000 to go. Here's a picture of K-nearest neighbor that explains why it's so attractive. You've got data. And trust me, these are 4 different colors, depending on the projector, depending on how your eyeballs work. It may not look that way, but there are 4 different colors there. And if I were to ask you, this new point here, A, what color should it be? Hey, looks like it ought to be purple. Because all the things around A, inside that circle, are purple. That's kind of dead center on that batch of purple stuff. Now, this one's off center in the batch, right? But the answer's the same. It's all red. This one over here, it's like 2/3 greens, and greens are kind of hard to see, and 1/3 red. So we might say kind of, I think Microsoft has struck here. Yeah, the mouse is there. Here we go. Okay. But we can say about C, for instance, that it's probably not purple. So we can still draw very interesting conclusions from this sort of thing. Nice and simple. Now, if we took that same data and it was scaled in a very non-propitious way, this is the same data. I just did the exponential on both axes. It can be really hard to see that data. So you have to understand your data, you have to present it in a reasonable way so that the obvious L2 metric, I mean, you could build a metric here. It gave you exactly the same nearest neighbor results, but it wouldn't be L2 anymore. But if you recast the data correctly, you can use L2 very nicely for it. So you definitely don't want data that looks like this if you're going to try to apply these modeling techniques. You'd rather have it look the other way. So there's limits to this.
On your problem with 25 million samples, how high dimensional was it?
Well, the spec was that they wanted it to be 10 to 100 dimensional. But in general, you can take very large dimensional data, and with the log of about the number of non-zeros in each data sample, you could project it down to that dimension without losing too much in terms of L2 metric. And so it's hard to imagine data that has a dimension whose log is greater than 100. Well, right now it is. But that's big. 2 to the 100th dimensions is just bigger than I worry about right now. And so 10 to 100 is nice. Also, if you do that projection, you change a problem that's heavily axis aligned, which is the way sparse data is, into something that's relatively rotationally invariant, which makes the L2 metric much more appropriate. And so, in fact, there are no real strong dimensional limits here if you're willing to pre-process in that way. So your mileage will vary. And you see these results as well. If you do L1 normalized or L1 regularized classifiers, the sample complexity of doing that learning is log of the number of samples. You only need the log of the number of samples, log of the dimension to do the learning on those classifiers. Whereas if you use L2 metric, rotationally invariant, you need linear sample complexity in order to do the learning. But of course, if you take that original data that's sparse, project it down into log of the dimension, then the rotationally invariant learning methods give you that same sort of property. So we depend on those properties, those invariants, in order to do that low dimensional problem. And the speeds that I quote in this are all at 10 dimensions, which happen to be the dimensionality of the customer. They originally had 30 some odd synthetic dimensions that they had extracted from real customer files, and they decided that 10 of them were interesting. And so we did that. So that's where I did, being a lazy dog. And the way we did this is kind of a cool thing. There were very strict IP limits. I couldn't touch their computers because I wasn't qualified to, and they couldn't really touch my computer. And there was questions that, there's an intermediary who handled the contracting. So did my company own the code? Did the intermediary own the code, or did the customer own the code? Well, we decided to avoid all those issues by working on synthetic data and make it all open source. So, the solution to this closed question is just make it all open. Nobody owns it, basically. Everybody can use it. And suddenly everybody was happy. It was a wonderful moment when suddenly being open had fixed all the closed problems. And so the goal is to build new open technology to facilitate proprietary solutions on top of that basic technology. The customer is very happy because they didn't feel like anything that had been published in open literature was something that they could build a proprietary business on, but they did feel like what variables they used and what objective target variables they used were highly proprietary, and that's where they could add value. So they, in the end, were quite happy with open technology there. And the ambitious goal was 1,000 speed up, but as I mentioned, really that meant 100 to 1,000x. And what's 100x speed up among friends, right? That's no big deal. Turns out it wasn't that big a deal, happily. So what we did is we took Mahout concepts and structures, and we built a whole bunch of new things that used the Mahout's ability to extend the math library very easily. And so we extended it to build what we call a delegating vector. It's just a tiny little wrapper that has a vector inside it, and all the vector-like things happen on the underlying vector. And then you can add in, you can mix in any additional properties you want. Like you might want to make it a weighted vector, or a centroid. And a centroid is a weighted vector, except it has a special kind of add operation, where you add a new vector into the centroid, increments the weight, and it uses Welford's algorithm to give you a progressive estimate of the mean. We also built a matrix implementation based on shared memory, which is cool to do in Java. uses MNAP to suck in very large, dense matrices, and it allows you to share these across processes or threads, which makes it very nice in a MapReduce setting, because the configure on each mapper object wouldn't have to suck in these 10 gigabytes of data. They would just suck in data that somebody else had sucked in previously, and that meant that we didn't have to penetrate the abstraction boundaries, and we could still get very high performance on moderate and memory size machines. You could have 24 gigabytes of RAM, you could run 10 or 20 threads of operation on it, and use only one 10 gigabyte memory. Critical, obviously, to making this work at large scale. Then we built some new kinds of search things. Brute force is brute force. It's the reference, it's the gold standard. Projection search, I'll talk about, but it basically projects down to a random direction and uses that to define an ordering and then search within that ordering. K-means search depends on a k-means clustering, and it searches nearby clusters and then does brute force or projection search inside those. LSH is a locality sensitive hashing that uses a hash which allows XOR to give us an approximation of distance, which then lets us only do the real floating point math on things that are almost certainly close. And then some very fast clustering algorithms. K-means, again, is a reference, but streaming K-means is the heart of this fast algorithm that I'm going to talk about. Here's projection search. We have data points, those are the black dots. And we have some random vector, that's the diagonal thing. And projection, orthogonal projection onto that thing has a nice property, a couple of nice properties. One, it defines an ordering. That's the beauty of one dimension. You have a total order. The other thing is that nearby points, points that are near each other, stay nearby. You know, there's got to be something about Las Vegas there. You know, what stays in Las Vegas or something like that. And occasionally you'll get faraway points that come together in the projection, which gives you a false positive sort of view of the world. And so if you have a query that you project onto the line, you can look just before in the ordering and just after. And if you look at enough things before and after, you will find the nearby vectors. And you will find extra crop. And so the question is, how much crop? And it's not that bad. You have within a small number there at 10,000 reference vectors, you have about a 20% chance of finding the nearest neighbor. And the vectors you do find, that's the nearest one, has a very small ratio of the distance as to the true nearest neighbor. Yeah?
So everything you found for this project is based on the synthetic data that you can have. Do you have any idea how it generalizes, the domain?
No, we did do that, and so every day we would test during the day on synthetic data, and we would I built a whole bunch of synthetic models which would kind of emulate a non-parametric universe, a Chinese restaurant process for picking cluster populations, and then various kinds of randomness to go into there. And we kind of tuned that random number generator to get results kind of like the real data did. But in all cases, everything reported here is on random data, and it was totally dominated by the performance on the real data. The real data performed much, much better, like 5 times as fast sort of thing, as on the random data. And that's as you'd expect. There's more structure in the real data, and so the world is better. And so, yeah. And so every day we would test on random data. Every night they would go back to the hotel, pass off to their India team, and they would test on real data on their MapR cluster. And then we come back the next day and we go, whoa, we're even cleverer than we thought last night. It was a nice feeling. But so projection search is a simple thing, and you can do it iteratively. And one of the real virtues of random projections like this is you defeat the curse of dimensionality. It doesn't matter what dimension you're projecting from, only what dimension you're projecting to, as long as you're projecting to a random vector. This is just so cool. So it doesn't matter what source dimension you come from, if you project into 10 random vectors, it's going to behave the same way. The asymptotics all depend on the number of projection vectors. And that's just a wonderful, cool thing. And so the goal here is purely to minimize the number of full-scale distances we have to compute. We use these linear projections to minimize that. So projection search is that one. And I actually used a Java-lang tree set to define on this ordering. So it's kind of a fun use of the weighted vector and drive that in with Google's magic construction of an ordering. And so there's only about 20 lines of code required to implement that, and it's in its core. I said all that, sorry. And the number of projections is really quite small. In this range that we're interested, 10 to 100 dimensions, you have at least a 10 or 20% chance of finding their nearest neighbor within a few points of the actual ordering. And if you do 20 of those, the chance of not finding the nearest neighbor is pretty small. It's like 0.9 or 0.8 to the 20th power. And that becomes small if you do enough of them. And what's even more important is the thing you do find is only going to be a little bit further away than the nearest thing. And so for a lot of purposes, it stands in just as well as the nearest thing. Or alternately, if you ask for a bunch of nearby things, the distribution of distances and the overlap with the true set is pretty high. The customer wanted at least 50% overlap and no more than 20% dilation relative to the true diameter of that nearby set. And that was easily met with these techniques. K-means search is a simple idea as well. You pre-cluster the data, and to find the nearest points, you find the nearest clusters, and you look at those. And of course, in that, you use a searcher, maybe a projection searcher, probably not a K-means searcher, because that would require you to search. Yeah, never mind. So here's data again. My data always looks the same, they're always round. And suppose we want to find things nearby there. And if we cluster those, that's the real K-means clustering of it. Here's the tessellation of the space according to what's closest. You can see that if we're going to do that search, we can just search those nearby clusters. Now this is much less true when you have really high dimension, but we don't have really high dimension by our assumptions. And it works very, very well. Gives you about 100x speed up in terms of the number of points you need to search to find good overlap with the correct things. And within each cluster, we can also get acceleration, which is relatively independent of the K-means searching. And so you can multiply these speed ups. And so if we get twice 100x speed up, we win, because we met our 1,000 goal there. Now the K-means algorithms that we used, we couldn't use Hadoop. We couldn't really use things like Kregel, because the iterations on K-means require us to scan the input again. And they also have very poor asymptotic convergence rates. The number of iterations goes up as the amount of data and the dimension goes up. So it's really, really bad. But there are recent algorithms to do with streaming K-means algorithms. The one here I used was out of University of Oregon and a researcher from Google. And they take one pass through the data. And if we want K clusters in the end, we use a much larger number, kappa, of clusters, which is roughly K times the log of n, the number of data points. We get that much larger set of clusters out in a very rough way. But there are nice bounds on how well those clusters, as weighted vectors, describe the probability distribution of the original data. And that probability distribution can then be clustered without reference to the original data, and it can fit in memory. So you make one pass, you get an approximation of the distribution of the data, you cluster that distribution, you're done. You have the clusters. You may want to make one more pass so you get the assignment of points to clusters. But in fact, you're done. You can run a really, really good clustering algorithm on that surrogate because it has very few data points relative to your original data. It's just really cool. And so you can run K-means plus to get good initial points. You can do some iterations, and you can use vol K-means to refine those clusters that you get, and you get something which has a very close bound relative to the ideal clustering, like 4x worse average distance, And that bound is very, very similar to the bound that exhaustive traditional k-means, as if you iterated through the whole data, gives you anyway. And so it's basically as good as you're gonna get, except you don't have to do the hard work. So it's a very cool algorithm. And the other cool thing about it is it's trivially parallelizable, because you can work on independent pieces of the data, get these PDF descriptions there, and then just take the union of those. You don't have to worry about overlap or whatever. Take the union of those, cluster that in memory. So break it into 10,000 pieces, run them all. They run completely without communication. The communication may have to do a few more steps of reduction, like you do in these basic algorithms, and then you just cluster. That's cool. I had no idea these algorithms were out there 6 months ago. The basic algorithm is very simple. We have a distance parameter beta there, which is kind of a threshold. Threshold we find by sampling the data a little bit. Just take the closest 2 points, and that's going to be our initial threshold. If a new sample is outside of the threshold, it's a new cluster. If it's inside the threshold, it's a new cluster with probability that declines linearly with how close it is. So if it's really, really close, it's going to go into the cluster. If it's halfway as far as the threshold is, then it's got a 50-50 chance of going into the nearest cluster and a 50-50 chance of going outside the cluster. Now we only needed one if there, so if this uniform rand deviate is greater than delta over beta, then we make a new cluster. Or we add the nearest, otherwise we create a new centroid. And if the number of centroids gets bigger than k log n, where n is the number of data points so far, then we will recursively cluster the centroids with the same threshold. And if the number of centroids collapses in that clustering, cool. If it doesn't collapse, we increase the threshold a bit so that we start getting this collapsing operation. And I have to admit that I have not gone through the mathematical argument well enough to explain it off the cuff like this. But there is a wonderfully simple, like 3-page long argument that this asymptotically has about the same performance as the raw k-means if you do that final cluster. You can't even take my word for it at this point. You have to take these unnamed authors. There's references are in the code. But it is a beautiful algorithm in that sense. So we get those large number of centroids out, k log n centroids out. Those provide the approximation. We can cluster those, or we can use the results directly. I mean, it's not a bad clustering, even as it stands. It doesn't have the proper bounds against the real thing, but it isn't bad. And here's how it parallelizes. This is a threaded version. This is a key practical consideration. How well does it parallelize? How well will it scale? The black line horizontally up there is the non-threaded version, just the flat-out implementation. It takes about 200 microseconds per data point. This is 1 million data points here. And obviously, it doesn't change with the number of threads we give it because it only uses one. The red and the blue lines represent the time taken for 2, 3, 4, and so on, up to 16 threads. There were 16 cores on the machine I ran this on, 16 physical cores. And so up to, and the gray line here is the perfect speed up that we could have gotten. And so you can see that's the log scale on the right, so it's a little bit misleading. You can see, though, it's very close to the gray line, out to around 10 or 12 threads. Once you get to that point, the number of threads that are in the background doing garbage collection, concurrent garbage collection, begin to interfere. We don't really have 16 cores available to us in a machine. We have somebody else will be using some of those cores to do I/O or to do this background garbage collection. So at around 12, we stop getting speed up. But essentially linear down to that point, and you can see where this 20 microsecond per data point claim comes from. That's on one machine. So if you think about it, it's pretty damn fast. 1 million data points clustered in 20 seconds. Kick ass. And parallelizable, as I mentioned, because this parallelization doesn't stop just at threads. There's no communication except for that final step, aka MapReduce. So we could do this on 100 machines.